finger's width away from where it's actually hit. Oh, it's there. Hello, room. Someone keeps resetting the settings on this computer, and I have to reset them to me. So I think somebody and I are annoying each other because of that. That's not how I want it to be. It's not doing that. Okay. All right, we want to go from polar form to rectangular form. That means we're going to replace r and cosine theta with x and y. Oh, I know.
What's that whistling noise?
You hear whistling?
Yes, but I don't know if it's just me.
Well, okay, then I don't know what the problem is. I'm sorry. I know when I plug speakers into my phone, it sometimes gets a high pitched hum or whistle.
Maybe it's my phone then.
So anyway, so since we have r equals 4 cosine theta, and I know r squared equals x squared plus y squared, and I know that r cosine theta equals x, then this needs to be squared and this needs to have an r in it. So if I multiply both sides by r, then I get r squared, so I can replace that with x squared plus y squared. And I multiply in here and I have 4 times r cosine theta, and the r cosine theta is now x. So this becomes x squared plus y squared equals 4x. What we need to do is, since we have x squared plus y squared, we know we have a circle. Because the standard form of a circle is x minus h squared plus y minus k squared equals r. Got ahead of myself. R squared, where h comma k is the center of the circle and r is the radius. So I need to transform this to look like this. So that means I need to bring the 4x to the same side and put it with the x squared. So now I have x squared minus, because I'm supposed to subtract 4x, minus 4x plus y squared now equals 0. Now it is not in what we call standard form yet. Do I have a purple? I need to have a purple. There's a purple. Where's my purple? There it is. So I'm going to group these together, the x squared and the minus 4, and I'm going to complete the square. Complete the square. So that will make this a, so I want to turn this into a perfect square trinomial, where I can factor quite nicely, because a perfect square trinomial is a binomial that's been squared. So to do that, we take whatever x is being multiplied by, and so that's a -4, and we take half of that. And once we take half of it, we square it, and that's what we're going to add in here and add over here, because if I add on one side, I have to add on the other side. So that's a -2 being squared. Please notice I keep this notation because I'm going to use this -2, this -2, it's going to become a -2. So, but -2 squared is a +4. And so we're going to add 4. So now we have x squared, Thomas, I swear. Some days I think my wife and daughter are correct. I'm losing my mind. Okay, x squared minus 4x, and now we're going to add the 4 here. And we still have plus y squared equals, and I have to add 4 to the other side, so 0 plus 4 gives us 4. And this is our r squared. So already I know r is 2. But now we have I divided the -4 by 2 to get a -2, because that tells me that's a -2 in there. And there I completed the square. Now, to get it to really look like this over here, what am I always adding or subtracting? Because subtraction is just a version of addition. I can write this y squared as y minus 0 squared Oh, this is what they're looking for, this right here. But this tells me what the center is. It's centered at 2, 0. And the radius is 2, right? Because this is r squared. With that, what?
Would it be 2 or -2?
It'd be 2. Because the radius is, it's always positive. Negative denotes direction.
The x would also be positive. The x?
But this, yeah, because it's x minus a number.
Oh,
And I'm subtracting the number 2, so if it was x plus 2,
it'd be
then I'm subtracting a -2. Okay. Good question. So what this looks like, we come out to 2 over here. And let me draw the circle first. I do better when I draw the circle first. My circles are never perfect, but at least they look better than when I try and make them work. So we have the circle. We have the y-axis and the x-axis. And we're going to say this is 2 units this way. And there's our circle. And they overlay this on the polar coordinates. So you'd have this circle, and then you'd have this circle, and then you'd have this circle. Actually, it goes through there. I'm mismarked here. So you'd have this circle, and then this circle. Because this would be out to 4. So, but me drawing it on the board just looks like a mess. And I haven't done that yet. Boy, I am just so scattered this semester. So we're gonna they're gonna solve it the exact same way, but they have a nicer picture than I do. And they don't explain how to get from here to here. And to here. And they don't have this down. But they do everything else I do. Except talk about we're using this is the equation of a circle. So multiply each side by r makes it easier to apply the formulas, because we know the formulas are that I had written was r squared is x squared plus y squared, and x equals r cosine theta. So this part here, the r cosine theta becomes x, so this is 4x over here, and r squared becomes x squared plus y squared. And they state that this is the equation of a circle. Proceed to complete the square to obtain standard form of the equation, which is what we always want to do. We always want to put it in standard form. If you have the equation of a line, you always want to put it either in standard form or in y or slope intercept form. If you have a quadratic equation, you always want it in descending order, where you have the x squared first and then the x and then the constant. So there are certain ways we want to write things. So you sometimes will get a minus a number, inside the binomial. If this was a +4 here instead of a -4, then this would have been a +2. Okay. Right? This was setting up the wrong class. Yeah, if you could just do it down to the end when you're done. Okay. Okay, this is standard form of equation of a circle with center 0, 2, 0, and a radius of 2. And then they didn't show it, they didn't graph it. Those Bohemians. Okay. So now we need to transfer this to rectangular, from rectangular form to polar coordinates. What does x equal in polar? What does y equal in polar? They when they solve this, they stop at a certain point where I would continue, but that's my personal preference. So what is x? What is x in polar coordinates? You tell me. It's something you probably should know already. We just used it on the previous problem. You can just see if anybody put it in chat. Because I know people in Zoom are a little reluctant to say anything on microphone. Especially if you're sitting in a place where there's other people and you got headphones on. So, x equals what? In polar coordinates.
Or cosine
Our cosine.
theta.
R cosine theta. So this is going to be 4 times R cosine theta. What does y equal?
Y cosine theta.
What?
Oh,
The y?
y cosine theta.
I'm not hearing.
Wouldn't it be the same thing? Or something?
No, y equals something different.
Y sine theta.
R sine theta. Remember from the unit circle where they said x equals cosine theta and y equals sine theta? Well, it's the same formula, it's just r is 1. Okay, so if you remember this, is an easy step to realize that you need to multiply by the radius. Because the radius of a unit circle is, lo and behold, 1. Hence the name unit circle. And this equals 16. Now, most times we want to get it down to where it's just one trig function. And we usually like it to be in sine, cosine, or tangent, but usually we like it to be in sine or cosine. So if I do the commutative property here, I have 4 times r squared times cosine theta sine theta equals the wonderful number 16. 16 is a binary number. It is 2 to the 4th power. It is 4 squared. And it is 2 times 2 to the 3rd power, which is 2 times 8. Okay. Just random thoughts going through my head this morning. Now, this part here looks like one of the trig identities, but it's missing something. What is it missing? When you're multiplying cosine and sine together, think double angle. Because I'm taking sine and cosine of the same angle. That's straight from the double angle theorem, double angle formula. But I'm missing something here. It needs to be multiplied by something. What's it supposed to be multiplied by? You're allowed to use the formula charts. So look under double angle. And look for where this is something equals something times, it's either cosine theta, sine theta, or sine theta, cosine theta. This is just a matter of using the commutative property multiplying. And so I have something times that. So what's happening over on this side? So under the double angle theorems, I'm looking for this situation, and there's something out here that's being multiplied. Any ideas? Do you have your chart?
Do I have it here? It's not here.
No. Okay. Anybody there have it? You should be where you can get to it. If you have your computer, you can go to files and test 2, and then the trig identities or the trig formulas. Trig formulas is where it's in.
Is it the number 2?
Okay.
Is it the number 2?
Yeah, there should be 2 here. And what does it equal?
Sine 2 theta.
Sine 2 theta. So I need a 2 here, but lo and behold, I have 4 over here. Isn't 4 2 times 2? I'm going micromanaging here with this. Well, I can just, because of the commutative property, I can just move this 2 over there. So now I have 2 times r squared times 2 times cosine theta sine theta. It still equals 16. The 16 is going to remain unchanged through this entire process. So this whole thing right here is just sine 2 theta. So now we have 2r squared sine 2 theta equals 16. Now, the textbook stops here. I would divide through by 2 to get rid of that 2 out front. And just have r squared sine 2 theta equals 16. Another way to write this is r squared equals sine cosecant 2 theta. Because you could, if you divided both sides by sine 2 theta, you get secant 2 theta. But secant 2 theta does not exist at certain angles where sine 2 theta does exist. So we would leave it this way. And I quit dividing through by the 2 because the textbook doesn't either.
How did you get from 4 to 2r squared?
All right, 4 is 2 times 2, correct?
Yeah.
And then I just took one of these 2's and I moved its position to be instead of 2 times r squared, I rewrote it as 2 times r squared times 2 times the cosine sine theta. So that's what I have here.
Okay, see.
So this is the double angle theorem, double angle formula. So that's why I factored 4 to 2 times 2, and that's how I got the 2 out here. Is that what your question was?
Yes, thank you.
Okay. Keep asking questions because I don't want anybody to be confused. Okay. And they do it without explanation. That's why I like to go over it first. So they're going to replace the X with R cosine theta and the Y with R sine theta. And they get the same thing we did at the beginning. And then they rewrote this as 4R squared cosine theta sine theta. And then they rewrote that. They didn't explain how come they wrote it this way. To go from here, whoops, wrong way, from here to here, but they wrote 4 as 2 times 2 and then brought the 2 over here and grouped this together because this is the part of the double angle theorem for sine. And where my preference would be to divide through by 2, they don't. Because now they move on to the next thing. Which is section 9.2, polar equations and graphs. This is the fun stuff. You have a graphing calculator, you put it in polar coordinates, and you can play with it. Okay. That's what I used to do. I have a calculator. I need to replace it because the screen is all messed up. You get those lines going up and down. It's just a mess. Anyway, it's old. I need to replace it. It graphs in 3D. It graphs X, Y, and Z. It's cool. I used to have fun with it. And then you could set it to spin, the picture to spin so it's moving. It's kind of cool. Anyway, identify the graph because you see those 3D pictures of graphs and stuff and they rotate. Well, that's what it will do. But it's not in color. So anyway, they might have a color version out. I haven't bought a new calculator that wasn't a scientific calculator in a long time. Well, since let me see, I've been teaching college for 12, 13 years now. So it's been at least that long. I used to keep up with the new TI calculators. I got the TI Inspire when they first came out with it. I went to a training and I got it for free. Yeah, I do all these. I used to do all this stuff and get a bunch of free stuff. I got a bunch of whole free stuff for the TI 84s. Something to hook up, to put on top of a overhead and stuff to hook into a projector and all like that. I don't use any of it, but I got it all for free. And it's all out of date now. Identify and graph polar equations by converting to rectangular equations. Well, there's only a few times where you want to do this. Most of the time, you want to do this part here is to graph the polar equations by plotting points, and then you graph it on a polar graph where you have those concentric circles. Okay. And you deal with the textbook deals with 30 degrees every pi over 6. Is it pi over 6? Yeah. So it'd be pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, and so that's how they do it. Or you could do every 15 degrees. So it'll be 15, 30, 45, 60, what is that? 60, 75, and 90. and then continue on around, but the more angles you attack, the more accurate your graph can be, but we're just looking at the shape. So identifying, we have a rectangular grid and then we have the polar grid. Notice they divided this up into 15-degree angles, pi/6. No, pi/12. Each one of these is pi/12 apart, which is 15 degrees. But the angles we typically deal with are these, along with the quadrantial angles. And then they tend to just use the 30-degree angles as well as the quadrantial angles. So, yeah. But sometimes the textbook uses more angles than that. So, you know, it just depends upon the whim of the author. Okay. Now, this seems obvious, but if it's obvious, we either need to have a definition that states it or a theorem that proves it. The definition we take to be true because this is what we say it is. And it works out for us. All right. An equation whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. That's exactly what happens with a function and its graph. So this is the same, this would be the same definition of a graph of an equation in rectangular form with rectangular coordinates. But we don't call it a rectangular equation because the first time you deal with polar coordinates is now. So in high school, you wouldn't have been introduced to this. Well, maybe if you had a more adventurous algebra 2 teacher or a trig teacher. Okay. Identifying graphed equation R equals 2. What is R?
3.
What?
3.
What? Yeah, the radius. So what is it saying? The radius of the circle is 4. So what does this graph look like? You just said it. What is it? If the radius is 4, then what is it? It's so basic. You're thinking it can't be that, right? But it is. It's a circle with a radius of 4. Here they want to convert the polar equation to a rectangular equation. So they're gonna square both sides. So they could get r squared here. And then they're going to square the 4. So r squared equals 16, but r squared is x squared plus y squared. And this is the equation of a circle with a radius of 4 that is centered at 0, 0. And there we have it. They start with an easy one that confuses a lot of people because it is so easy. Okay. Any questions on this? that the polar equation r equals 4 is just a circle with a radius of 4 that is centered at the pole. Right? Everything comes off of the pole. And so if you have an angle, then it's off the polar axis. But there's no designation of what theta is, so theta is whatever angle. Just so long as the radius is 4, the angle is on this circle. It'll hit this circle. It's kind of like y equals 4. Every x value is there's no x value because every x value gives you a y of 4. That's the same thing here. Every theta value gives you an r of 4 on this graph. Now, we call this a function because the definition of function changes because we're dealing with polar coordinates, not rectangular coordinates. Identify the graph of the equation. All right, now there's no r, so the radius could be positive or negative. It's just the angle has to be this angle. Let me see how they do this. Convert the equation to a rectangular equation. So what are they going to do here? Well, they're going to do tangent to both sides. Okay. Because we know that tangent equals y over x. So y over x equals this, whatever this number is. What is this number? Tangent of 3 pi over 4. What is the tangent of 3 pi over 4? Three pi over 4, I keep going back to the unit circle. 3 pi over 4 is this angle here. X and y, what do you know about x and y?
Square root of 2 over 2. And square root of 2 over 2.
Almost,
1 over is negative that.
it could, because you're in the second quadrant,
The x is negative.
the x is negative. So the x and y are opposites. So when I divide opposites, what do I get? What do I get when I divide a negative 3 by positive 3, or when I divide 17 by negative 17? Because that's what you're doing. You're going to divide opposites.
Negative 1.
-1. So this is y over x equals a -1. Right? Because tangent is x over y, because we're going to convert to rectangular. So now we just multiply both sides by x. This is called a direct variation. Y equals a -x. Y, well, that's this line. Y equals -x, goes right like that. Y equals x and x equals y. They're both one of the 45-degree angles. Or two of them taken in pair. Okay. And that's what they show you. They don't go through such a deep. So yeah. Tangent equals y over x, and tangent of 3 pi over 4 is -1. And so y over x is going to equal -1, and so y equals -x. And I think they do a graph of it. I think they do show the graph of this one. There it is. Now, R can be positive, because this ray here is the ray they're talking about. But R could be positive or R could be negative. So you're either going this way or you're going in the opposite direction. So there we have it. Because we have no stipulation on what R can be, so R can be going in the same direction as the ray or in the opposite direction. What is R sine? R sine theta, what does that equal? Y. So this becomes y equals 3, which is a horizontal line where each of the y values is 3. So R sine theta equals 3. It's going to be perpendicular to the y, to the theta equals pi over 2. Because it's tangent to the circle R equals 3 at that point. But every point along here, if you do the radius times the sine of that angle, you're going to get 3. And they formalize this in an upcoming slide. So our cosine theta equals -4. Well, that's a lot like this one, except it's cosine instead of sine. So guess what this is going to look like? A vertical line. So, because cosine theta is x, so that's x equals -4. So it's 4 units to the left of the pole. 4 units left to the pole is where that vertical line is. Just like on the other one was 3 units above the pole. It's a vertical line that was 3 units above, where this one is 4 units to the left of the pole, a vertical line that's 4 units left of the vertical pole. I mean, left of the pole. So here's the theorem that covers those 2 examples. Because we have 2 more examples that would show the other 2 situations. One where A is negative for sine. We dealt with when it was A, and then the other one where A is negative. And then here we did one where A was negative. And it also deals with when A is positive. So if you're dealing with R sine theta, if A is positive, it's a horizontal line above, A units above the pole. And if A is negative, then it's the absolute value of A units below the pole. And same thing with cosine, if it's R cosine theta, but it's going to be to the left as A is negative, and to the right if A is positive. And it's going to be a vertical line so many units away from the pole. Now we want to graph this. Right, hint, hint, they say it's a circle. All right, so they're gonna multiply both sides by r. And get r squared equals sine theta. R squared equals 6r sine theta, so r squared, so x squared plus y squared equals 6y. And then we do the same thing we did before, which is complete the square. So we're going to subtract 6y from both sides. And then we're going to complete the square here. So that means the x value of the center is 0. And the y value of the center is going to be a positive 3. But we need to convert that. So I take half of -6, which is a -3. -3 squared is 9. So we're going to add 9 to both sides of the equal sign. So what's inside here is a perfect trinomial, is a perfect square trinomial. So it's going to be y minus 3 being squared. So 9 is the radius squared. So now we're going to have a circle that is 3 units above a circle with a radius of 3, where its center is 3 units above the pole. Right. The point 0, 3 corresponds to this point, which is 3 units above the pole on theta equals 2 pi. And then the circle goes like that. So r equals 6 sine theta is that circle. Now, I want you to do the same thing here, but please notice, since it has a -4 here, it's going to be below, it's going to be to the left of the pole. Cosine is in the x direction, and so it's going to be to the left of the pole. And it's going to, we do it the exact same way we did the previous problem, by multiplying both sides by r and then replacing r squared with x squared plus y squared, and replacing our cosine theta with x. And so we get x squared plus y squared equals a -4x. And then we do the same process we did before. Well, this is the same. This is the same. No, it's not the same, because the one we did before, it was a positive 4x, but now it's going to be a plus 4x. And so what we have here is going to be x plus 2, where before we had x minus 2. And so that means the x coordinate is negative. And so that means we're to the left of the pole, 2 units. And now we're going to have a theorem that covers both the 2 equations dealing with sine and cosine, and whether it is negative or positive. Because if it was positive, if that was a positive 4, then it would have been over here. And like on the previous one, it was a positive 3, but if it was a -3, it would have been down here. Okay. And that's what the next slide is talking about. R equals 2 sine theta. The radius is a, and it's centered at 0a. -2a sine theta. The radius is a, and it's centered at 0 negative A. So the negative sign belongs with the A, not the 2. And with the cosine, you have the same thing. And all of these deal with A being a positive real number, okay? So that one that said 4 cosine theta, then it's gonna be 2 times a negative 2 cosine theta, where the negative 2 is the radius. Okay, and each circle passes through the pole because the radius is the same as the distance from the pole. So that means it hits that point over there. Okay. Now we talk about symmetry. We have 3 situations to look at as far as symmetry is concerned. We look at, are the points symmetric? Is it symmetric with respect to the polar axis? Is it symmetric with, which is the horizontal line, x equals 0, I mean y equals 0? Is it symmetric with the line theta equals 2 pi, I mean pi over 2, which is the y-axis, x equals 0. And then we talk about, is it symmetric with respect to the pole? That means the 2 points could have the same theta, but opposite radii. So 2 pi over 2 and negative 2 pi over 2. So that would be this point and this point. They're symmetric across the, or with respect to the pole. And there's ways to test for symmetry. Is an equation symmetric with respect? Does an equation have any symmetry? Well, well, we'll look at that. So symmetry with respect to the polar axis, if you replace theta with negative theta and you get an equivalent equation, in other words, you get back to the original equation, then it's symmetric with respect to the polar axis. That deals with cosine. To have symmetry with respect to the line, oh, they don't have it here. What happened to it? Well, it's this line, 0 theta equals pi over 2, which is the y-axis. Why don't they have? Anyway, I don't need to worry about that right now. Then the polar equation, if you replace theta with pi minus theta, and it works out to be the same equation. Once you simplify it, then it's going to be symmetric with respect to the line theta equals pi over 2. Now, oh, and then for to test for symmetry with respect to the pole, you do both of these, but you do them separately, because this or here is not inclusive, it's exclusive. It's either you replace r with negative r, or you replace theta with theta plus pi. You do one or the other. Well, you actually do both of them if this does, if doing this one doesn't show symmetry, then you do this one, because one might show symmetry and the other one doesn't. Or they both might show symmetry, so you check both of them. Then it's gonna be symmetric with respect to the pole. And here's the deal. Just because it failed the test, you tested for symmetry and no symmetry showed up, doesn't mean it doesn't have symmetry. Because it could fail both of these tests for being symmetric with respect to the pole, and it still be symmetric with respect to the pole. So failing the test doesn't mean it doesn't have symmetry. It could still have the symmetry. This just says if it passes this test, it does have that symmetry. All right, every circle has all three of these. So an equation could have one or more of these three types of symmetry, and these are the three types of symmetry we check for. Because there's other forms of symmetry, but we're centering on things that go through the pole. Okay, so they want you to check for symmetry first. So the first thing to do is to replace theta with negative theta. Does it wind up being the same equation? So now, what sign of negative theta? The sign of a negative angle is what? Sine is an odd function. F of negative x equals what? Yeah. So sine of negative theta is the negative. Yeah. Sine of negative theta is the negative of sine of theta. So I'm subtracting, and I wish they had put that here. I'm subtracting a negative sine theta, which means I'm adding sine theta, which is a different function than this one up here. So it failed the test. That doesn't mean it doesn't have that kind of symmetry. It just says the test says it doesn't have it definitively. Now we check for symmetry with respect to theta equals pi over 2. And we replace theta with pi minus theta. Yeah, from my perspective, that looks like a 0. Can you see that it's a theta? Yeah, I know it's a theta, it's just, yeah. That's why I wish I had the controller for that thing so I could move the lens to point down a little bit further or up a little further. Anyway. So now I go back to my formula chart and look at what sine of alpha minus beta is. So the sine of the difference of two angles equals, what is it? Sine, is that one's sine alpha, cosine beta, sine, cosine alpha, sine beta. And it's with sine, if it's minus here, it's a minus between the two products, which is what they do. So it's sine of the first times the cosine of the second minus the cosine of the first times the sine of the second. Well, what is sine of pi? Unit circle again.
Negative 1 comma 0, sine is 0.
Yeah, this point over here. That point is negative 1, 0. Yeah, so sine is 0 here. So this is gone. What's cosine here?
Negative 1.
So this is minus a negative 1 sine theta, or minus a negative sign, which is a positive sign, but I'm subtracting, so
1 minus sine theta, which
One.
proves the.
oh, they went in, okay. Sometimes they show this step, they don't always show this step. And so inside the bracket, you have minus a negative, which is just sine. And so then you just have 1 minus sine theta. Because this disappeared and this became positive. And it's 1 minus that sign. And so, yes, we wound up with the same equation. Right? The test is satisfied, so the graph definitely has some symmetry with respect to that line, to the vertical angle. And then we want to check for symmetry with respect to the origin, because it could possibly have that as well. So we're going to replace r with negative r. And then multiplying both sides by negative. Well, r doesn't equal the same thing, so it fails that test. And so then we replace theta with theta plus pi, and we do the same thing again. Okay. But now it's sine times cosine theta plus cosine theta times sine theta. Well, sine of theta, sine of pi. Sine of pi is still 0. Oh, wait. But this one is this is negative 1, so this is a negative sign in here. So this has disappeared, and so you get minus a negative sign because that's 0 there. And so you don't wind up with the same function, so it is not, or the same equation, so it is not, it fails that test. Doesn't mean that it's not symmetric to the pole, but the test doesn't show that it is. It is symmetric with respect to y to theta equals pi over 2. So I'm just going to look at the angles over here. And if this point is on it, then across this angle here, I just find it's a matching point over there. So if it's here, then I just find its matching point over here. So I'm just gonna, and what the textbook does, they go from they start from negative pi over 2, and then they go to negative pi over 3, and then they go to negative pi over 6. They skip the 45-degree angle, and then they do 0, and then they do pi over 6, and then they do pi over 6 times pi over 3, and then they do pi over 2. And so we build the table. We have theta, because when we're going to put the angles into the formula, And the formula is R equals, what is it, 2 times 1 minus the sine of theta. So this involves a little bit of calculator work as well as remembering the unit circle values for these angles. So theta is, we start with a negative pi over 2, and then we're going to go to a negative pi over 3, and then a negative pi over 6, and then 0, and then pi over 6, and then pi over 3, and then pi over 2. The y value for negative pi over 2 is -1. The y value for negative pi over 3 is a negative square root of 3 over 2. The y value for negative pi over 6 is -1/2. The y value for pi over, well, now it's just going to repeat these numbers, except they're going to be positive. So now this is +1/2, and this is the positive square root of 3 over 2, and this is +1. So I'm going to do 2 times 1 minus a -1, which equals 4. So this goes down, so when I graph that, draw circles. Damn, I did good this time. Wow, okay. There is some deflation over here, but that's okay. And so at negative pi over 2, we go down to 1, 2, 3, 4. I always graph these points as I find them. And we have this angle and this angle and this angle and that angle, and then we have the polar opposites. And now at negative pi over 3, that's going to be 2 times 1 minus a negative square root of 3 over 2, right? Which is 2 times 2 plus the square root of 3 over 2. And so those go to 1. And so that's just 2 plus the square root of 3. And you type that into the calculator. Excuse me for a moment. Now, when this is approximately 3.74. So I come out 1, 2, 3.74, which is about here. And its mirror image is over here. Oops. Okay. I can graph the mirror image as I'm following. If I'm on the line pi over 2, then there's no mirror across because it's on the line. And then at negative pi over 6, my y value is 1/2. So this is 2 times a negative times 1 minus a negative 1/2, which gives me 2 times 3/2, because this becomes 1 plus 1/2, which is 1.5, which is 3/2. And then the 2's go to 1, and so that just gives me a 3. So at negative pi over 6, we're at 1, 2, 3. and its polar, and its image across that vertical line is over here. And then at 0, the sign value is 1. I didn't put that here. So the sign value is 1. So we get 2 times 1 minus 1, which is 0. Is that right? Yeah, so that comes all the way back to 0 here. How does that happen? Oh, I know what's going to happen now. Okay. And so now at pi over 6, it's going to be 2 times 1 minus 1/2. Well, 1 minus 1/2 is 1/2, and 1/2 times 2 is 1. Well, that wasn't right. This isn't right. At 0, it is 1. 1 minus. Okay. So if this comes out to 1, and its image is over here. I did something wrong. What did I do wrong? Because this isn't the picture it's supposed to be. And then we have pi over 3, which is square root of 3 over 2 for the sign of that. So we have 2 times 1 minus the square root of 3 over 2, which is 2 times 2 minus the square root of 3 over 2, which is 2 minus the square root of 3, which is approximately I don't remember. That's why I did it wrong. Sign at 0 is 0. So far it's gone around like this and around like this. And now at pi over 3, it's at, what was that? I saw it and then I forgot it. 0.26. So this is approximately 0.26, which is a fourth of, almost a little past a fourth of the way going that way. And so the mirror image is over here. And at pi over 2, the sign is 1. Okay. And so this is 2 times 1 minus 1, which is 0. Right? Because 1 minus 1 is 0 and 2 times 0 is 0. And so then we do wind up down here. And so it looks like this. And this is the first time I've ever drawn this on the board, and it looked decent. Be amazed at my skill. Okay. This is known as a cardioid. It's a cardioid because it looks like a heart. Okay. And that's what they did over here. They found all these values. And then they graph those values on the graph. And so they basically did the same thing I just did. So we graph this point, it's on the line of symmetry, so there's no image for it. We graph this point, its image is over here. We graph this point, its image was over here. We graph this point, its image is over there. The image of this point is over there, and same thing with these two, and this one is on the line, and we just follow them as we found them. Now, I could have done all the pi over 12 angles all the way around, and got a more detailed look at what was going on there, but it's not necessary. It's just keeping straight in your mind what is happening there with those values. Definition of cardioids. Cardioids. I always pronounce it wrong. I always say cardioids, but it's cardioids. Cardioids. An android. So if R is A times 1 plus cosine, or A times 1 minus cosine, ours was this, the one we graphed was this one. And if you have plus, then it's going to look like this one, except it's going to be top to bottom. It's still going to be symmetric about the pi over 2, but it's going to be like this shape now for this one. And when it's cosine, it's like it's laying on its side. And this one is going to be like this. And this one's going to be going the other way. Where with this one, the top is on the positive side, to the left, to the right of the pole, and with this one, it's to the left of the pole. So you have those situations with these forms. So understanding what those are, and what the shape looks like. Depending upon A, affects the size of it and also a little bit of the shape.
No big red stick? No big red?
Oh, I have some in the bag.
Oh.
I have Big Red, and I have Dr. Pepper with cream soda, and I have
For the energy.
the orange dreamsicle. That's the main reason I get it, because it tastes like a dreamsicle, an orange dreamsicle. It really does. Okay. Now, it kind of looks like this. Was it plus or minus? Plus. It kind of looks like this, but it isn't. It isn't. It is 4 plus 2 times cosine theta. So it's, I can't factor 2 out of this and say it's 2 times 1 plus cosine. It's not the same thing. And notice the name they give it. Limacon, I don't know how that C is pronounced. I don't know what alphabet that comes out. I don't know if it comes out of the French alphabet. I don't think it's Spanish. It could be out of the French or some Middle Eastern, or who knows what the hell. I don't know alphabet. I barely know my own. Okay, so they're going to check for symmetry. So they're going to replace theta with negative theta. And boom, that shows symmetry with respect to the polar axis. Right? Because cosine of negative theta is the same thing as cosine of theta. So it does have it does have symmetry with respect to the polar axis. So we know it does have that. And then replace theta with pi minus theta. And so you do the subtraction, cosine of the difference of 2 angles. So it's the cosine times the cosine of the 2 angles plus the sine times the sine of the 2 angles. And cosine of pi is 1 and sine of pi is 0. And so this gives us, no, cosine of pi is negative 1. And so this becomes, and this term drops away, so this becomes not the same formula. So it fails that test. So from initially looking at it, it probably isn't symmetric with respect to the vertical line, but we don't know. Replace R with R, R with negative R, and they don't go through and show this, but they're saying that the test fails for these two. So when you replace R with R, it's not the same formula. When you replace theta with theta pi plus theta, the test will also fail. So the graph may or may not have symmetry with respect to the pole. And as you graph this thing, you will find out what's going on here. All right, so the symmetry is with respect to the polar axis. So we only need to check these angles from 0 to pi, and that's what they do. They went from 0 to pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 3, 5 pi over 6, and pi. So the 30, 60, 90, 120, 150, 180. And then they just punch, so cosine of 0 is 1, cosine of pi over 6 is square root of 3 over 2, cosine of pi over 3 is 1/2, and so they replaced all those, and then they just, basically you punch it into the calculator. And so the top half, all right, you start over here at 6, and then it's going to be at 5.73, which is about there. And then, well, that's a little too low. There. And then at pi over 3, it's at 5. Brings us to about there. And at pi over 2, it's at 4. And then at pi over 3, it's at 2 pi over 3, it's at 3. Radius is 3. A little bit further out. And then at 5 pi over 6, it's at 2.27. So at this one, it's going to be about here. And then at pi, it's at 2. So this half of it kind of goes like that. And so I do the mirror image here, and I do the mirror image here, and the mirror image here, and then the mirror image here and here. Whoops. So it has the same shape on this side. So my points were off. What can I supposed to do? Okay. I wasn't doing, and mine's a little deformed because I freehanded it a bit. And so you graph the top half, or, yeah, mine's a little wonky. You can graph the top half and then look for the opposite points, or the mirror images, or you graph them as you graph the point, you graph its mirror image, graph this point, graph its mirror image, graph this point, its mirror image, this point, its mirror image, and this point in its mirror image, and then you just draw it in. And it's another cardinal. Oh, this is a limacon without an inner loop. So it looks like a cardioid, but it's not. The point up here is not on the pole. With cardioid, the point will be on the pole. Okay. And so now we talk about having A and B values. This was 4 minus 2 cosine. Or was it plus? Was it plus? Yeah, it was plus. 4 plus 2 cosine, where I don't know which one they say is A and which one is B. Because they switch them up on me. So yeah, okay, A plus B. Okay, this is where A is greater than B. Without an inner loop. Are characterized equations of this form, where you have plus or minus the cosine, plus or minus the sine. When it's cosine, it's going to be symmetric across the polar axis. When it's sine, it's going to be symmetric across the theta equals 2 pi over 2. And in these cases, all 4 of these cases, the number is larger than the number than the coefficients of the cosine. So we had 4 plus 2 cosine theta. So the A is larger than the B. So this is a situation. Now, what happens if the A and B are reversed, where the A is smaller than the B? Well, then you have one of these lamacons with an inner loop. An inner loop looks like that. So we have those situations. Okay, so this one, it's going to be symmetric about the polar axis, checking for symmetry. We wind up with the same formula. Okay. And we get a different formula because it was plus, but now it becomes minus. And with and they don't go through this one, they just say the test fails in those situations. So once we graph it, we can tell if it has those 2 symmetries or not. And they do the same thing. since it's cosine and since it's symmetric about the polar axis, then we're just looking from 0 to pi. And so then we can just, look for the image across the polar axis. And so that's what they did. They graphed all those points. Did they go all the way to? Wait a second. Yeah. Please notice that 3 of these measures ended up being negative. So although we're going to go to 2 pi over 3, which goes this way, but because it's a negative 0.5, we're going to end up going this direction. So we're going to wind up at what is that? 5 pi over 3. Okay. So this point is the negative 0.5, 2 pi over 3. And this point is the negative 0.16, negative 1.6, 5 pi over 6. So it winds up going the opposite direction of that ray down to here. And this one wound up being negative 2 pi. So instead of going out 2 units in the pi direction, we come back in the 0 direction. And so you graph all those points, and then you look for their polar, for their image. So this one is going to be here. And this one is going to be, see, 1, 2, 3, 4. So that one's going to be here. And this one's going to be here. This one's going to be up here. And this one's going to be here. And it's going to wind up here. So this one's going to come like this. Which we have here. And we're past time. And the next slide is just going to show us the formulas for when you have an inner loop. That's where the B is larger than the A in all of these. So it's the exact same formula. It's just which is larger, the A or the B. Okay. So next time we'll start here. And we have a new shape to look at. It's called a rose. I usually call them flowers, but they call them roses. All right. Well, take care. You too. Okay, I'm gonna go ahead and close the window. Because I got a class in 10 minutes, so I'll see y'all next week.